In this video, we will introduce you to the graphs of rational functions, which include what are rational functions, what are the characteristics of their graphs, and how to sketch these graphs. So, what are rational functions? Recall that when we refer to rational numbers, it means that the number can be expressed as a fraction. For example, 3/4, 4/5, 7/2. And irrational numbers are numbers that cannot be expressed as fractions, such as pi and e. So for a rational function, it is a function that can be expressed as a fraction, where both the numerator and denominator are polynomials. Some examples of rational functions are given over here. We can easily see that both the numerators and denominators are polynomials, and the highest power of the numerator can either be smaller than, the same as, or larger than the denominator. However, depending on the relative orders of the numerators and denominators, we should classify rational functions as either proper or improper fractions. This is the same as in normal fractions. If the value of the numerator is smaller than the denominator, for example 3/4 or maybe 7/20, this fraction is what we call a proper fraction. Whereas if the denominator is smaller than the numerator, for example, if I have 7/2, or they may be equal, such as 5/5, these fractions are what we call improper fractions. For rational functions, we say that a rational function is proper if the order of the numerator is smaller than the order of the denominator. And it is improper if the order of the numerator is the same as or larger than the order of the denominator. And if we encounter an improper fraction, we must always perform long division first to make it into a proper fraction. The process of performing long division is slightly similar to how we perform long division for numbers. I will demonstrate the process of long division of a rational function through this simple example. First, I will write the division in this form, which is similar to how we perform long division with numbers. The numerator goes inside the bracket and the denominator goes outside the bracket. Next, we want to eliminate x squared in our term, and how we can do so is to multiply an x to x minus 3, such that we get x squared minus 3x, which is to be subtracted from x squared plus 3x. So if we perform this subtraction, we will end up with 6x, and next we are going to bring the 5 down such that we end up with 6x plus 5. Next, we will need to eliminate 6x, and how we can do so is to introduce a 6 at the top, because 6 multiplied by x minus 3 gives us 6x minus 18, and the 6x will cancel out nicely for us. So now we have 6x plus 5 subtracted by 6x minus 18, and this gives us 23. And we note that the order of this final value of 23 is less than the order of x minus 3, and therefore we can stop the long division process. And with this, we can write the simplified form of our rational function as x plus 6, where the quotient comes over here, plus 23 over x minus 3. 23 is the remainder, which goes as the numerator, and x minus 3 is the denominator. In example 1, we are asked to express this particular rational function as a proper fraction. And so let's perform a long division. First, let's write down our two terms, 3x squared plus 2x minus 5 within the bracket, and x plus 1 outside. So now I know I need to eliminate 3x squared, and how I can do so is to introduce a 3x, because 3x multiplied by x plus 1 gives me a 3x squared, and the 3x squared will cancel out nicely. So I will have 3x squared plus 3x, and I put a minus sign outside. This subtraction will give me negative x, and I'm going to bring the 5 down, so minus x minus 5. And now, in order for me to eliminate this negative x, I will need a minus 1 on top. and this gives me minus x minus 1, which I need to subtract it from minus x minus 5. And therefore, this leaves me with negative 4. And we are done with the long division process, and therefore, this rational function can be expressed as y equals to 3x minus 1 minus 4 over x plus 1. Next, let us turn our focus to the sketching of rational function graphs. The usual ingredients of such graphs include the asymptotes, where the graph approaches but never intersects at infinity, such as this horizontal and two vertical asymptotes. Note that it is still possible for the graph to intersect the asymptote and finite values. For example, we may have a graph that looks like this. This is the horizontal asymptote, and our graph may go from minus infinity up, cuts the horizontal asymptote, and makes a U-turn back towards the horizontal asymptote. Next, another essential component of a rational function graph are the axial intercepts, i.e. the points of the graph that intersect with the x and y axis. Lastly, another component of a rational function graph are the turning points. We shall now look at how to obtain these characteristic components in a rational function graph. To determine the equations of all the asymptotes, we must always rewrite the functions as proper fractions. And once this is done, we can easily extract the equations of the asymptotes. Firstly, the quotient part of the proper fraction becomes the equation of an asymptote. In the H2 syllabus, this equation is either a constant or a linear term. So when it is a linear term, we get an oblique asymptote, and when it is a constant term, we will get a horizontal asymptote. Next, if we solve for the root of the denominator, the root will become an equation for the vertical asymptote. Now, how did we arrive at these two simplifications? Let's take a look at a simple example of y equals to 2x plus 1 plus 1 over x minus 3. Imagine what happens when x goes to infinity or negative infinity. So as x tends to infinity or plus minus infinity, 1 over x minus 3 will become very close to 0. And what this means is that in this equation, the last term over here goes to 0, and the remaining term over here, which is your y equals to fx, is the dominant term when x goes to plus minus infinity. On the other hand, if we let the denominator go to 0, that means x minus 3 becoming 0 or x becoming 3. What happens is, for our same equation of y equals to 2x plus 1 over x minus 3, this term is going to become undefined. That means the entire equation is going to be undefined for x equals to 3, and therefore we can see that the root of the denominator must give us a vertical asymptote. For examples 2a straight to 2d, we will be looking at the same equation, y equals to 2x squared plus 3x plus 1 over x minus 2. And in this part of the example, we are asked to determine the asymptotes of the graph, and therefore we will first need to change it into a proper fraction form. And how we can do so again is by long division. So let's perform our long division. 2x squared plus 3x plus 1 divided by x minus 2. We need a 2x outside, and this gives us 2x squared minus 4x, and therefore we have 7x plus 1, and we need a plus 7 outside. We have 7x minus 14, and therefore we end with 15. So we know that this equation can be written as y equals to 2x plus 7 plus 15 over x minus 2. And we can say that y equals to 2x plus 7. It is the oblique asymptote. Whereas x minus 2 equals to 0 or x equals to 2 gives us the vertical asymptote. Next, to find the axial intercepts, we know that either x or y must be 0. For the y-axis intercepts, x is equal to 0. So graphically, if I have a graph that looks like this is the point that we are looking at for the y-axis intercept. And based on this, we see that x value must be equal to 0. Similarly, for x-axis intercepts, which is this point over here, y must be equal to 0. And therefore, we can simply substitute x and y equals to 0 and solve the resulting equations for the corresponding axial intercepts. In example 2b now, we are asked to find the coordinates of the axial intercepts. So let's find out our y-axis intercept first by substituting x equals to 0. We will end up with y equals to 2 multiplied by 0 square plus 3 multiplied by 0 plus 1 divided by 0 minus 2, which gives us a minus half. And we can find out the x-axis intercepts by substituting y equals to 0, which gives us 2x squared plus 3x plus 1 divided by x minus 2 equals to 0. And therefore, we can simplify it into 2x squared plus 3x plus 1 equals to 0, since we can simply cross multiply the denominator across. Since 0 multiplied by anything is 0, we can just throw away this x minus 2. Factorizing this remaining quadratic expression, we will get 2x plus 1, x plus 1 equals to 0. And this tells us that x is equal to minus half or x is equals to minus 1. And therefore, we have three axial intercepts now: 0, minus half, 0, and minus 1, 0. Usually, for turning points, if the question doesn't specify that we give the exact coordinates of the turning points, we can use the graphic calculator to determine turning points. So usually, we can sketch the graph out first, then see if there are any turning points. And if there are turning points, use the GC to determine the coordinates of these turning points. Now, we are asked to determine the coordinates of the turning points of the same graph. And if we sketch this graph out using the GC, we can see that there are two turning points. And therefore, we can simply make use of the maximum or minimum calculation function in the GC to give us the coordinates. So we know that negative 0.739, 0.045 is the maximum point, and 4.74, 22.0 is the minimum point. And both of these are from the GC. With all the characteristic components determined from examples A to C, we can now sketch the graph with all the corresponding details. So first, let's draw our axis. Next, we will first draw the asymptotes, which is at x equals to 2. Remember to label all the asymptotes as well. And we have y equals to 2x plus 7. It doesn't have to be to scale as long as you show all the characteristics properly. Okay, next we have the axial intercepts, which are at minus 1, minus half, and there's a maximum point somewhere in between here. Also, the y-axis intercept is somewhere over here. Next, the other turning point that we have lies somewhere over here, and therefore we can connect all the dots over here to get the shape of the graph to look like this. Now let's combine everything that we have learned to draw a graph of the rational function from scratch. Okay, we are given this function of y equals to 2x squared plus 2x divided by x minus 1 divided by x plus 3, which we have transformed into a proper form for you so that there is no need for us to perform partial fractions and long division. So we know that y equals to 2 is the horizontal asymptote. And the vertical asymptotes are x equals to 1 and x equals to minus 3. After we determine the asymptotes, the next thing to do is to find out the axial intercepts. So we are going to first substitute x equals to 0. We will end up with y equals to 0. So I know that the graph passes through the point 0, 0. And we are also going to check if there are additional x-axis intercepts. When y equals to 0, we get 2x squared plus 2x divided by x minus 1, x plus 3 equals to 0, which becomes 2x squared plus 2x equals to 0, which is the same as 2x multiplied by x plus 1 equals to 0, and we get x equals to 0 or minus 1. And therefore, we know that 0, 0 and negative 1, 0 are the axial intercepts. Next, we want to find out the turning points of the graph. So let's key into our GC and we obtain this graph over here. So what we can see now is clearly there is a turning point located somewhere near the origin, but please be careful because if you zoom into this part over here, it is actually another turning point which may easily be missed out if you are not careful. So now let's zoom into this part by changing the windows to these values over here, and we see that once we zoom in, we can clearly see another minimum point over here, and therefore we can find out these two turning points respectively. So the maximum point near the origin is at negative 0.464, 0.134, and the minimum point is at 6.46 and 1.86. And now, with all the information found, let's try to construct our graph. First, let's draw the axis. Next, we are going to draw the asymptotes, which is at x equals to minus 3 and x equals to 1. And we also have another horizontal asymptote, y equals to 2. Next, the axial intercepts, 0, 0 and minus 1, 0. And we also have turning points at negative 0.464, 0.134 is somewhere over here. And another turning point at 6.46, 1.86, which is somewhere over here. So therefore, if we combine all this into a single diagram, we will end up with a graph that looks like this. Now that we know how to sketch rational function graphs, let us take a look at a very common question type. That is to find out the range of validity of a rational function. For some rational functions, if we sketch the graph out, we can easily see that for some y values, the graph do not exist. For example, in this graph, between the two turning points, the graph does not exist. We are then asked to find out what is the range of values such that the graph do not exist, and usually it is through an algebraic method. This means that we cannot use the GC to determine the coordinates of the turning points. The way to handle these kind of questions is to make use of the discriminant, i.e. b squared minus 4ac. Similar to simple quadratic equations, we can solve for b squared minus 4ac less than 0 if we are interested in the range of values that do not exist. But now, we will have to rewrite the rational function into a quadratic equation first, and the variable y becomes part of the coefficients of x or x squared. Once we solve this inequality, the solution to this inequality becomes the range of values that y does not exist. Let's use example 4 to illustrate this method. So we are given the equation of y equals to x plus 1 over x. The first thing we want to do is to cross multiply the denominator across so that we get normal polynomial equation. So I get xy equals to x squared plus x plus 1, which I can rewrite as x squared plus 1 minus y times x plus 1 equals to 0. Now note that this becomes a quadratic equation in terms of x, and from here I can perform b squared minus 4ac less than 0. So I will have b squared minus 4ac less than 0, which is 1 minus y squared minus 4 times 1 times 1 less than 0, or if I expand, I will get y squared minus 2y plus 1 minus 4 less than 0. On simplification, I will have y squared minus 2y minus 3 less than 0, and I can factorize the term on the left to become y minus 3, y plus 1 less than 0, and therefore if I solve this inequality, I will end up with y between minus 1 to 3, and this is the range of values of y that the graph does not exist.